Today, I would like to talk to you about new techniques that we've been developing at the University of Potsdam, along with my co-authors Bodo Buchhagen and Ayosha Reinwald. And these techniques are for clustering of river profiles. And I'm going to show you some examples of how we can apply these techniques to both real landscapes, where we have high-resolution topographic data, and then also to synthetic landscapes from numerical modeling. So the topic of our brainstorming this morning is on combining topographic data with numerical models. And Irina gave us a really nice talk on Tuesday about some of the ways that we can actually integrate topographic data into these models. So I'm going to take a slightly different approach in my presentation today. Instead, I'm going to use these models as a way to validate new techniques for analyzing topographic data. And then test it on a numerical model. In this case, I'm going to be talking about a landscape evolution model, which allows us to have an idealized landscape where we fully constrain the history of the landscape. And then once we know that the method is doing exactly what we can expect, then we can apply it to real topographic data. And the question that I'm going to be asking in the presentation today is an extremely general one. And that is, how do landscapes respond to external forcing? And what I mean by this is, does the morphology of the landscape record some history of tectonic or climatic perturbations that we can detect? And I'm going to be focusing on channel gradients, which has been done many times in the past, because we might intuitively expect that channel gradient in some way reflects the tectonic or climatic history of a region. But we know just from observational data that channel gradient decreases simply as a function of distance downstream along a river system. So this is just an example from the River Tralligill in the Highlands of Scotland, where I'm from. And you can see in the headwaters, we have very steep gradients, and this decreases as we go downstream to the outlet. So if we want to compare channels with different lengths, we need to somehow normalize this gradient for this distance downstream effect. So a common way of doing this is to plot for a river the channel gradients on the y-axis against the drainage area on the x-axis. And empirical observations have shown that there is often a power law relationship between these two variables. Therefore, we can fit a linear regression through this data and extract a y-intercept, which will give us some kind of called the channel steepness index, which we can think of as channel gradient normalized for this drainage area. And many studies have shown that this channel steepness correlates to uplift rate in many landscapes, for example. So this is all well and good, but what do real data actually look like? Well, this is an example of a typical slope area plot from a river on the Lith Plateau in China. And I want to point out kind of two problems here. One is that there are significant gaps within the data in drainage area space, which is just because of the branching nature of river networks. So each one of these represents a jump at a tributary junction. We also have lots of noise in the slope data at a single drainage area. And this can either be due to inherent noise within the DEM or geomorphic noise, such as the presence of alluviation within channels, for example. So you can imagine if we want to fit one linear regression through this data, it's very difficult to extract a meaningful channel steepness for this system. A second problem, which I'd like to focus on today, is that of landscape heterogeneity. So in order to illustrate this, I'm showing you here the results of a very simple landscape evolution model, which is just run with fluvial processes, but we have random patches of different rock types. You can see these here as these kind of weird-looking square patches. And I'm going to show you one of these slope area plots for basin 2 here, which you can see drains both the hard and the soft lithology. So in this slope area plot, you can see rather than having this nice linear trend, we have significant heterogeneity, which is resulting from this change in lithology. So you can see if we were to fit our linear regression through this data, the channel steepness that we would extract would not be representative of either portion of the landscape. So what I'm going to suggest to you is that a potential solution for this problem is that we can cluster the river profiles before we extract these channel metrics. This will allow us to separate out channels with different morphology and kind of clean up the extraction of these channel metrics. So what do I mean by these clustering algorithms? Well, the inspiration for this comes from the analysis of time series data, where we have some kind of metric which we measure at a series of different spatial locations, and that varies through time. The point of these clustering algorithms is to kind of group these profiles into groups where the profiles behave simultaneously in time. And the point of these algorithms is really to reduce the amount of data that we have if we have a large number of these profiles, and to get some kind of signal from the noise. And the algorithm I'm going to be talking to you about today is called an agglomerative clustering algorithm. And I want to just briefly run through how it works. So you can imagine that we have 6 data points. So these could be time series, they could be river profiles, and they're located at a certain distance from each other, where this distance represents how different the profiles are from each other. So the closer these points are located, the more similar the profiles are. And we start off by each profile being in its own group or cluster. And then in our first iteration, we merge the points which are closest together. We can represent this in what's called a dendrogram, where on the x-axis we have these points, and we link them together using the y-axis, where this distance represents how different those points are. The algorithm then continues this operation iteratively, where we keep merging the points which are closest together, until we end up with just having one big cluster or group left. You can see this has allowed us to build up this dendrogram over time, which tells us how each profile is related to every other profile. In this case, we've ended up with 3 groups at the end: a red group, a purple group, and a blue group. I just want to give you an example of how this has previously been used for an environmental context. And so this is global clustering of time series of sea surface temperatures, where the points here are colored by the cluster number. You can see this allows us to kind of group global pixels into areas where warming occurs at a similar time of year, for example. And we can really allow us to see patterns where you imagine if we took each one of these points individually, it would be very difficult to see any relationship. Okay, so how can we apply this to river profiles or generally to geomorphic studies? Well, what we can do is in our time series data, we have time on the x-axis and some kind of metric on the y-axis. For our river profiles, we just replace this time axis with a distance along profile axis, where 0 would be the channel head, and then we're going downstream. And as our metric, we use our channel gradient. So what we're doing is really grouping profiles based on how the gradient varies as a function of distance downstream. But it's really important when we're doing this for river channels that we separate out channels which have a similar discharge or drainage area, so that we can make sure our comparison of slope data is comparable. So to do this, we first of all separate the network by stream order. So we can first of all extract profiles for all of the first order streams, cluster these. Then we can cluster all of the second order streams, and then all of the third order, etc. And this allows us to really look at clustering profiles in different parts of the landscape, so we can do each part of the catchment separately, for example. Okay, so now I want to show you quickly how we can test this method. So first of all, I'm going to show you an example from a model landscape where we have varying lithology, just to prove that this could work in an idealized case. And then I'm going to show you an application to a real landscape from Santa Cruz Island off the coast of California. Okay, so there's going to be a video here, which I'm going to jump to in a minute. But I just want to kind of quickly go through the setup of the model. So it's going to be a simple square model domain, where we have just fluvial processes, and we run it for 100,000 years. And in the north part of the domain, we have harder rocks and in the south part we have softer rocks. And there's around a factor of 5 difference between the two. So let me just switch to the model. So you can see that dissection in the landscape occurs very quickly in the south, where we have these soft rocks, and then it takes place much more slowly in the north with the harder rocks. And I'm going to show you the results of these clusterings from this basin here, which in the north drains this harder lithology, and in the south drains this softer lithology. So I go back to the presentation. So this is the results of the clustering for this basin here. And this is just the clustering of all the first order streams in the catchment. The rest of the river network is shown in white, where the first order streams are colored by the cluster. You can see that we've detected 2 distinct clusters in this landscape, a red cluster and a blue cluster. And the division between these clusters occurs exactly at where this boundary between these lithologies is. So this is very reassuring. It shows us that we're kind of getting what we should expect. But just to emphasize that this approach is purely data-driven. We put no information about the lithology into this method beforehand. So just to show you what we can get from this algorithm, we can look at the dendrogram, which, if you remember, shows us how each profile is related to every other one. Where this distance here represents how different the profiles are. And you can see that the 2 distinct groups or clusters separate very nicely, so they're very distinct from each other morphologically. Once we have the profiles, we can then do our slope area plots separately for each cluster. And this allows us to fit a linear regression through this data and get a channel steepness for the channels in each separate cluster. You can see in the red cluster here, which drains the harder rocks to the north, we have a channel steepness of around 0.1, whereas the blue cluster in the softer rocks has a channel steepness around an order of magnitude lower than this. You can imagine if we plotted these data together, our channel steepness value would not represent the channels in either part of this landscape. I just want to point out these profiles here, which don't fit nicely onto the curve. And I think these profiles are the ones which are crossing this lithological boundary. So we get some kind of landscape transience here from this change in lithology. Okay, so that's our model landscape. And now I want to show you an application to a real landscape. And here I'm showing you the Pozo catchment from Santa Cruz Island off the coast of California. And this catchment has a complex sea level and tectonic history, which I'm going to completely ignore in the talk today, and just show you the lithological map. So here in the south of the catchment, we have the Canada Shale, which is a very weak lithology. And then in the north, we have a breccia and 2 volcaniclastic units, which are much harder. To show you the surface expression of these lithologies quickly, in the Canada Shale, we have extensive gullying and more smooth, effusive hill slopes. And whereas in the breccia and the volcaniclastic units, we don't see as much gullying, and we generally have higher relief. This is the result of the clustering for the Pozo catchment. And you can see again, we have 2 distinct clusters, a red cluster and a blue cluster. And most of the profiles from this weaker shale unit all cluster together in red, whereas the profiles from the harder units all cluster together in blue. Although there is some noise in the data, which we can expect as this is like a real landscape with high resolution data. This is a 1 meter DEM. Again, we can look at the dendrogram for these profiles and see that these are very morphologically distinct. They have a high distance between them on the dendrogram. And if we do our slope area plots again for the different clusters, we can detect that in the weaker shale lithology in red, our channel steepness is around half that of in the harder units, which are in the blue cluster. This really allows us to distinguish these areas of different channel steepness well within the landscape. So just to give you a quick summary and maybe some thoughts for the brainstorming, I think this clustering technique is a really good way in which we can tackle this problem of landscape heterogeneity, which affects basically every landscape on the Earth. And this approach is a really data-driven approach. It's got very few assumptions about the data, and certainly no assumptions about the geomorphic processes that are going on. And I think we can use this as an exploratory technique, first of all, separate out different parts of the landscape that we then want to analyze in more detail. I think it's got many potential applications beyond that of which I've shown here. So for example, we could look at hill slope to valley transitions, extraction of alluvial reaches, extraction of debris flows, for example. And I hope that I've shown as well that we can use numerical models as a way to test these methods and before we apply them to real landscapes to make sure that they're properly doing what we expect. So that's me. Thank you. Questions for Fiona? Come on, thanks for initiating that.
My questions are necessary. That's great. But what about trying differential rock uplift? Do you think that would also be something discriminated with clustering?
Yeah, so something I'm working on at the moment is running some models where we have either simulating a fault through the catchment or having a series of base level falls and propagating some nick points into the catchment and seeing if we can get different clusters above and below these nick points or above the fault. I've also tried this for an area in Idaho where there's a really pronounced nick point and I can get really good clustering of the profiles above and below the nick point. So I think it could be used to kind of separate out different areas of landscape transients pretty well.
One clarification.
Yeah.
Do you have to tell the algorithm how many clusters?
No. That's really dependent. So that's calculated into it, but you do need to give a threshold on the difference between in order to kind of select a number of clusters, which can be tricky to do. So I've come up with a kind of statistical way of doing it, which I didn't have time to go through, but I think there's a case to be made for doing it based on a kind of depending on how many clusters you think are appropriate in terms of like a process-based explanation of the landscape. So. Any other questions? Yes.
Maybe a very naive question, but how do you convert the imagery data into data as it amenable to the algorithm?
Yeah, so what we do is we take our raster of the elevations and we first of all extract a channel network, and then we have the source point of each network, and we basically use a flow routing algorithm to follow that down to the outlet, and then we have a series of points along the profiles from which we can get the slope and the distance.
Those are standard conversion tools, or other tools that you have?
It's a combination of using kind of standard tools that are available and then kind of adapting it for use for this specific technique.